All right, hi. I'm going to be working through some quizzes so that we can get you guys ready for the test. All right, let's not waste any time. You guys should be seeing my screen right now. Let's go ahead and move on. All right, so this first question right here, all right, which substances H2Br2 or HBr are present in the highest concentration at equilibrium? All right, well, that's obviously pertaining to this reaction that they give us right here, H2Br2 and 2HBr. Now, if we're looking at the highest concentration, it's either products or the reactants, right? And if it's at equilibrium, then we're looking at our K constant, not our Q, because that's not at equilibrium, but our K constant. And lo and behold, right here, this is our K constant. Give me 1 second. Oops. Okay. And let's just redefine our K constant. All right. So for K constant is products over reactants. All right. And our Kp value is 3.5 times 10 to the fourth. That's a very large number. And if it's a very large number, then P must be very high and obviously R must be very low. So if that's the case, there are more products than there are reactants. And what is our product? HBr. This is higher Kp value equals higher products. All right, let's move on down. So we can consider reaction from problem 1 again. Calculate the Kp for the following reaction. Well, right here we notice, all right, well, what's different from the first reaction is right here, they flip-flop these. On top of that, look at the coefficients. They're half of what they were in the first reaction. So on top of that, we have our reciprocal rule, 1 over Kp, and our new Kp is also to the half power because it was halved. All right, if I don't know why this keeps coming up. All right. Hopefully that won't keep happening. But if we were just to combine these, it would be 1 over K1 half. All right. And let's just plug in our Kp value of 1 over 3.5. Yeah. Times 10 to the fourth. All right. Math is already done. Our new Kp value is 5.3 times 10 to the negative 3. All right. All right. Let's move that back down. So right here, they're giving us concentrations of both products and reactants. All right. And it's asking, all right, is this reaction at equilibrium? If not, what direction will proceed? Well, this directly correlates to our Q versus K concepts, right? Because if Q equals K, then it must be at equilibrium. All right. So let's go ahead and solve this out. All right. So right here, it gives us 0.315 and 0.15, and those are of our reactants, so they're going to be at the numerator or denominator, my bad. And 0.05 of our product, which is the numerator, right? So let's put it in 0.055 of our HOCl, and don't forget your coefficients right here, so the second power. 0.315 atmospheres of H2O, which is 2, the first power, times 0.15, is also to the first power. And if we multiply that out, our Q value is 0.064, which is less, I'm underlining, that's not equal to, but it's less 0.09. All right. If our Q value is less, remember our Q value, kind of like our K, is product over reactant. And if it's less than that, then there's not enough product and more reactant than there should be. And if there's not enough product, well, then it must shift right in order to get more product. So shifts to the right. Needs product. All right. Okay, so for part 4, it's giving us, all right, at a particular temperature, 8 moles of NO2 is placed into a 1 liter flask and NO2 decomposes. And at equilibrium, this is the concentration of NO, one of our products. So if we're looking at our analysis of this and we're trying to solve for K, let's do an ice table. So we have 2NO2, 2NO, and then O2. all right? Our initial concentration, well, we just start out with 8 molarity, because remember 8 moles per 1 liter. Whoops, 1 liter. And it doesn't tell us that we start with anything in regards to the products. So those are 0, and the direction is pretty clear. It has to go towards products, okay? So if it has to go to the products, we have minus 2x. Do not forget your exponents, not exponents, your coefficients during the test. That is the biggest small mistake that people will see. Plus 2x and then plus x, right? And if right here, if it's at equilibrium, it's at 2.0, then 2x equals 2, and x must be 1 molarity, right? All right. So let's complete this out. So if x is 1 molarity, then 2 times 1 molarity, that's 2 molarity, minus 2 molarity is 6 molarity at the end. Then plus just 1 molarity, because just 1x is just 1 molarity. All right, and then we just plug it back into our equation. So our products on top, 1 molarity, that's our O2, 2.0 molarity to the second power, all over 6 molarity to the second power, because don't forget those coefficients. If you multiply that out, just simple arithmetic, we have 0.11 as our Kc value. Oops. Kc value. All right. Okay. K5. All right. So for this reaction, we are given a Kp value and all of that. Calculate the Kc for the reaction at 45 degrees Celsius. Now this goes back to just directly plugging and chugging it into one of our equations. And our equation that we're looking for is K P Kc times R times T delta N. If we're given our Kp, that's 1.9 times 10 to the third. Our R values just are simple, I believe is 0.0821. All right. Our temperature, if we convert 45 degrees Celsius into Kelvin, what do we get? That is 318 Kelvin. And our delta N, that's only related to gases. So if we have 3 moles of gases here, 2 moles of gases here, delta N is final mole versus initial mole. That should be final product. So it's going to be 2 minus 3 equals -1. Let's put it all together. 1.9 times 10 to the 3 equals Kc times 3, 18 Kelvin times 0.0821 to the -1. And we just solve for Kc. Our Kc is just 5.0 times 10 to the 4th. All right. All right. Pause the recording real quick. All right, sorry about that. Let's go back to our screen. Okay, so you guys should see this. Let's continue. All right, so right here, consider the following reaction, and you see right here, we are given a Kc, so we want to solve for it, right? And if it gives us 0.15 molarity of Br2 and 0.15 molarity of Cl2, those are our reactants. And they're allowed to come at equilibrium. So let's go ahead and draw our ice table, okay? So Br2, Cl2, 2 BrCl. We have 0.15 molarity, 0.15 molarity, and this is going to be 0. Now, since the product, there are no products present, it must go toward the product. Just fill in that void. So pretty easy. So we know that this is going to be plus, this is going to be minus, this is going to be minus. Now, in terms of x, we just use our coefficient. So there's a coefficient of 1 here and 1 here. So it's just minus x. And right here is going to be 2x because of that coefficient. So at equilibrium, we should have 0.15 minus x, 0.15 minus x, and we should have 2x. All right. Now let's go back here to our Kc. So our Kc equals 0.2, and we know that that's our relative abundance of product over reactant. Okay, so 0.20, let's just plug in what we have at our equilibrium, because remember K, or the concentrations at equilibrium. So we have 2x, and don't forget our exponent because it is to the second power. And yes, they do stack. So we already have like the 2 in the coefficient and 2 in the exponent. They're both there. And we have 0.15 minus x. But notice how there's 2 of them. And instead of just multiplying it by 2 or buying it by itself, we'll just put that exponent there. And you'll see why. Because if you have an exponent up here and an exponent right there, you can square root the entire thing and get rid of both exponents. All right. So let me get those numbers up. There we go. There we go. So our numbers will be 0.447 equals 2x over 0.15 minus x. Now for this, it's just basic algebra. We just solve for x. So if you bring this over, let's fill out that algebra just a little bit more. Let's use green. 2x equals 0.0671 minus 0.447x. Let's add this 0.447x, 0.447x. All right, 0.0671 equals 2.447x. And our x, if we solve for it, is 0.0274 molarity. All right. And that's just our x. That's not our concentration of BRCl. Because remember, BRCl is at 2x. So we just multiply that by 2. All right. And our new final concentration, 0.055 molarity. That is a concentration at the very end. Now let's look down here. All right, so for this hypothetical equilibrium equation, we have 2a going to b and going to c. The Kc value is 1.6 times 10 to the negative 12. Now that should ring some kind of bell because that is an extremely small Kc value. Excuse me. And that means that the relative abundance of products over reactants is extremely small. It's not going to dissociate pretty much at all. So the numerator is going to be significantly low, while the reactant or the denominator is going to be very, very high. So keep that in mind. All right. There they are. Okay. So if we write this out, let's draw like our hypothetical ice table again. So if we have 1 liter of a flask where there's 0.5 moles of A and no B or C, there's none of that. And our concentration of A is 0.5 moles over 1 liter. That's just 0.5 molarity. If we were to draw the change in the ice table, that's going to be minus 2x because of our 2 coefficient plus x is going to be x 0.5 minus 2x. And if we were to draw out our expression or our equation, 0.5 minus 2x equals I'm blanking here, 1.6 times 10 to the negative 12, right? This is going to be pretty much negligible. Same thing with this x, because it's just going to be so small. All right. So if it's going to be very small, there's going to be a lot of reactant. So there's going to be a lot of A. All right. If there's a lot of A, it's just like there's going to be a lot of, well, our equilibrium concentration of A. It's just like subtracting our 0.500 molarity minus 2 times, let's say 0.0000001. It's probably even smaller than that. If you're subtracting that much, it's really negligible. So it's pretty much just going to be like 0.5 molarity. And that's why our correct answer is B. All right. Let's move on to our bonus question. All right. Which of the following equilibrium reactions has an equilibrium constant expression with no concentration or pressures in the numerator? Write the equilibrium expression for that reaction. So remember, our numerator is going to be the products, because if whatever our expression constant is, our product's going to be in the numerator. Now, if that's going to be 0, there has to be no product, specifically no gaseous or solution or solvated aqueous products. Because remember, solids and liquids are not counted in equilibrium at all. So we're basically looking, all right, which one of these has no gas or aqueous solutions in the product? And there's only one answer. That's right here, A, because those are just a solid and liquid. Because for B right here, there's a gas. That would be in the product. There's a gas right here, and there's an aqueous solution right there. That will give us a K constant value, but right here is just going to be 0. All right, so we stop recording now. I'm about to record quiz 5.